Good afternoon. Right, welcome to CPD sessions with Altecnic. We'll be walking through system balancing today. So first of all, a bit of housekeeping. So welcome and thank you for joining Altecnic CPD Day. We'll be delivering this in partnership with the Cibse West Midlands. Cibse West Midlands region arm is to expand the knowledge of its members through the various lead learning initiatives, and we hope you find today's topics insightful. As a bit of courtesy to myself and the other participants, if we could politely ask all delegates to mute when not talking, please, so we minimise that background noise, and to know that anything written in the chart can easily be seen on the call. There'll be a time for a Q&A at the end of the CPD. If you can write these questions into the chat box or use your raise the hand function, please. Following today's CPD, you'll be issued with a certificate of attendance. Thanks very much. So let's move on to our topic for this afternoon, system balancing. So here we go. Strap yourselves in, guys. So the course objectives today, we're going to look at constant volume systems, the basics behind that, variable volume systems, again, some of the basics covered, pump sensors and pumps and sensor positioning rather, balancing of the system itself, and finally a summary to go through everything we've picked up on. This is quite a wide topic, so we're not going to cover absolutely everything today, but certainly definitely the basics. So constant volume systems. So we've got basically, yeah, it is what it says on the tin. You've got some cons and pros as we go through these. Manual balancing, the increased energy use in the system, increased number of control valves, the terminal unit as bypasses as well, lengthy and time-consuming commissioning process. We'll explain a little bit more on that later, and the control of flow only. Some of the pros on that: simple control valves to use, easy to understand, and they literally do exactly that, control the flow only. There's a little diagram there for you to see, usually a 3-port system. So variable volume systems, again, we're going to run through some pros and cons. Multiple control methods, multiple control valve types. They're more complex. The pump requires specific control methodology, but the flip side of that, you've got huge energy savings. The pump flow and return are matched to system demand, so you can use slightly smaller pump sizing, smaller pipe sizing. Constant systems run at full demand all the time. So the pump law relationship, having the flow and return, equates to about 1/8 of the power. Reduced thermal losses and the control of the flow and pressure. Reduction in the capital cost, as we mentioned before, reducing the number of control valves, the terminal unit bypasses as well. Automatic or self-balancing, therefore it's simplified to commission. This is the key part of understanding constant volume and variable volume systems. So constant volume systems, why have we got a balance and how to calculate that pressure? Fluid takes the path of least resistance. We all know water's a bit lazy. Unbalanced circuits can lead to overflows or demand overflow. Overflows are an occupant discomfort. Distant circuits are starved and often uncontrolled. Circuits need the energy centre to see the excessive flow. There's a couple of examples on the right-hand side there of an unbalanced circuit and set into the percentages. As you can see, the top one, it's getting less and the bottom is getting more the closer we get towards that energy centre, and you can see that as a percentage overflow. So the concept of proportional balancing. Balancing is dependent on the basic principles. The adjustment of a valve in a sub-circuit alters the flow not only in the sub-circuit but also in other circuits within the system. As such, an adjustment reduces the flow in the sub-circuit, then the flow elsewhere must increase as total mass of flow rate is constant. The percentage of the total flow in each branch remains constant irrespective of that mass flow rate. So as we look through to that, you can see here, the hydraulic balancing of an existing system can reduce consumption by up to 35%. Little graph there for you to look through. Hydraulic balancing systems energetic consumption compared to the global consumptions. As you look there, you've got it. You can see the massive difference between the two. Move across. And we've got a couple of examples coming up now of balancing valves, the types commonly used in systems. So we've got manual static balancing valves there. So you've got double reg valve, flow meter, balancing valve, a DPCV, and radiator valves. Some of these different radiator valves obviously manufactured by ourselves. So balancing procedures. This is where we start looking at the labour, intensive labour side of systems. Before balancing, check that the pipework is complete and pressure tested. The system is flushed and clean. Strainers remain clean after 24 hours of continuous operation. That's quite key. And air is vented. All valves are fully open, and any 3-port valves are on full flow. So when setting up a system, these are all key basics that have got to be remembered. So a nice little diagram there for you guys to have, if you can zoom into that, on their constant volume systems, little layouts. An example of this constant volume system, you've got multiple 3-port control valves, you've got double reg valve bypasses, the commissioning sets on the terminal units and on the branches, and as well as on the lateral. So it's quite valve heavy. And the commissioning process of this, therefore, means a lot of legwork for the installer and the commissioning engineer. So you've got to set position 1, and then walk back, set position 2, check again, set position 3, check again, so on and so forth, until you've got the proper proportional flow rate for the system. So you can see that's quite a lot of man hours, a lot of walking backwards and forwards. So you imagine on a 20, 30 story building with multiple terminal units, it's going to take quite a bit of time to balance that system up. So, and again, if we look at that in pump energy, so we've got the graph here as well. Again, I won't dive too much into this for you guys, but you can see the power savings involved. And you compare this to a variable volume system. An example of a variable volume system, you've got 2-port control valves as opposed to 3 ports, PICVs, pressure independent control valves, orifice plates on the branches and the laterals if required. And the commissioning setup on a variable volume system should be a lot more straightforward. So we can control our pump pressure at the index, so the weakest point of our system. And if we can hold, in this particular case, 40 kPa at that furthest point, everything before will at least have our 40 kPa. Quite important on something, for example, with a HRU system, you might require a minimum pressure for the valve, for the control valves to operate or the plates to operate correctly. Failure to hold that index type design can lead to inefficiencies or inactive units within the system. Methods of control valves in variable volume systems. So as we picked up on just, you've got DPCVs, manual balancing valves, and fan coil control unit valves, ABVs, FCUs, and PICVs. PICVs being pressure independent control valves. And again, an example of the system layout and where the valves are used within these systems. Example of the DPCV there for you. Quite often used on the return with the partner valve on the flow. Holds the differential pressure downstream of the valve. Can be adjusted or fixed, often supplied with a partner valve, for example, the Cleffi 140 series DPCV, linked with a capillary tube there so as you can get the pressure set across the valve correctly. A couple of pros and cons with the DPCV. They are fixed or adjustable differential pressure, the adjustability of the valve itself. A single valve can protect multiple terminal units or laterals on systems. Simple product, can be located away from the terminal unit for servicing. Less susceptible to problems with any dirty systems. There's a couple of cons with them. Increased cost time of installation. For example, the capillary tube allows for setup. The adjustable valves, so they can be tampered with. People tend to meddle with them if the system's not running correctly. A capillary tube can easily be damaged. It's only a small bore. And it requires a control valve for the terminal unit, and therefore the increased cost of that install, as we saw before on the constant volume system, multiple valves, multiple commissioning points. As an example of an automatic balancing valve with FCU on the system. Moving on slightly to a newer version, sort of the automatic balancing valves, quite prevalent across systems now. Constant flow rate regardless of the differential pressure. Pressure ratings ranges of sort of 7 to 1,000, 15 to 200, and so on and so forth as we go across, all measured in kPa. Above or below the pressure range, the valve acts like a fixed orifice, so the flow rate will increase as the DP increases. The Cleffi 121, 125, 120 and 193 series examples of these. We'll just move on to looking at how the cross-section of the valve operates. Text is a bit small on these ones, guys, but you can clearly see under certain flow rate characteristics, depending on the differential pressure required, so the minimum DP required, will alter your flow rate. You can do this usually by a Venturi device, as you can see there. The minimum working pressure on this example, 15 kPa. You can see the control valve range with the initial DP right the way across to a fixed DP point. Over and above that, your flow rate is going to fluctuate. Well, obviously, that's down to how the valve has been sized in the first instance. There's a few pros and cons with automatic balancing valves. Fit and forget operation, difficult to be tampered with, so it's good for servicing points. Relatively low cost, install on the terminal unit and no other control valve required on the system. Long life if the service is clean. The cons to this sort of system setup, the cartridge needs to be removed for flushing, so that can be a labour issue. Has to be manufactured to a specific flow rate and designed per terminal point. The flow rate is fixed and cannot be adjusted and can be affected by any kind of dirt or debris within the system. That's to be fair, clean of any valve on a system will be affected by dirt or debris. An example of the system with the pressure independent control valves, so PICVs. Again, quite similar setup to the DCVs. You look across here, we've got an example of the Cleffi valve here. The combination valve, DPC with diaphragm, it's a completely settable flow rate, and various different options for actuators or operational on and off modulating heads. And the series that we use is the 145, 146. Again, if you run through a few pros and cons with the DPCV, it's a complete solution, so no other control valve is required. Ease of installation, can be preset and locked. Less space required for installation and various control vent head options. Prone to blockage on dirty systems, and the longevity of the valve. Plus, they're not the cheapest thing in the world. If you consider it's effectively 3 components in one, that would give you a clue as to why. Cross section there of how a DPCV actually, a PICV actually works. The device itself regulates the flow rate by changing the bore across the section of the control. Affected by the delta P, so that DP, that's the DP part of the valve, keeps it constant across the device. But it's important that these are sized correctly. So automatic balancing using a PICV, the device to keep the flow rate constant independently from the circuit's differential pressure conditions. The total of the differential pressure, so P2, P3, must be in the range for the minimum DP of the valve and the maximum value of 400 kPa in this case. Again, you can see the sweet spot there. And looking at the control head options, you have linear and linear proportional actuator there. Also has the ability to isolate the valve when required. Yeah, so the on-off version. And if we consider these when you're looking into terminal units and the flow rate management and the control of risk, an example there of an older way of doing it perhaps. Multiple valves, multiple joints. You can see the amount of time it would take an engineer to install that and isolate and insulate the whole unit afterwards, versus perhaps a more modern way of looking at things with the terminal unit. with a flow module. It's got a combined valve module itself, so it's more compact. Heating and cooling options are available, and includes the integral PICV control, a strainer, a drain and air vent, on-off modulating heads, and it's fully encapsulated in a clamshell type insulation series 149. Can be installed in multiple orientations, as you can see there on the right. Something which is widely available in our market now. Just a little bit of a summary there for you guys. Balancing has to be addressed. For constant systems, commissioning sets and DRVs, a high number of valves are required. It's labour intensive for commissioning, sort of an older way of doing things. Variable volume systems, definitely more up to date. Control valves have to be matched to the terminal point, to the FCU curve. Various balancing methods available. DPCV systems are less efficient. DPCV systems are less efficient and generally more valve costly. Any of the ABVs are less labour intensive to install, but the FCU control valves are still required. A PICV system are flexible, should be more low cost, give a better control, and do not require any additional fan coil unit control. The fan coil unit management module, integrated PICV, controls the risk of this even further. Hopefully that's been of use, guys. We're available for questions now, if it helps.